There is a place on Earth where the rules stop making sense. It's not in a remote jungle or at the bottom of an ocean trench. It's buried in the countryside along the border of France and Switzerland, hidden beneath fields that have been farmed for centuries. On the surface, you'd see nothing unusual. Maybe a few low buildings, some gravel roads, the occasional truck pulling in and out of a gate, but 100 meters down, something is happening that has no precedent in the history of our species. A machine is peeling back the fabric of existence, layer by layer, and what it's finding underneath is making the people who understand it best deeply uncomfortable. The machine is called the Large Hadron Collider. It's the largest and most complex scientific instrument ever constructed. Its main ring stretches 27 kilometers in circumference, a circular tunnel so large that it crosses an international border multiple times. Inside that tunnel, protons are accelerated to 99.99999% of the speed of light. They circle the ring 11,000 to 245 times every second. And when they collide, they don't just smash together like billiard balls. They obliterate each other, converting their kinetic energy into a spray of particles that haven't existed in any natural form since the first microseconds after the Big Bang. The temperatures at those collision points reach 5 trillion degrees Celsius. That's 400,000 times hotter than the center of the sun. The energy density is so extreme that the protons themselves cease to exist as coherent objects. They dissolve into their constituent parts, quarks and gluons, which briefly form a state of matter called quark-gluon plasma. This plasma existed for only the first 10 microseconds of the universe's existence. The collider recreates it 40 million times every second. Here's what makes this relevant to you. The data coming out of those collisions is not matching the predictions. Not by a lot, not in a way that would show up on a casual glance, but in ways that are consistent, reproducible, and pointing in the same direction across multiple independent experiments. The rulebook that physicists have used to describe the universe for the past 5 decades is showing cracks, and the cracks are getting harder to ignore. The rulebook is called the Standard Model of Particle Physics. It's a mathematical framework that describes every known particle and 3 of the 4 fundamental forces. It's been tested to an accuracy of 1 part in a billion. It predicted the existence of particles that weren't discovered until decades later. It is, by any reasonable measure, the most successful scientific theory in human history, and it is incomplete in ways that are becoming impossible to paper over. Let's start with what the Standard Model can't explain. Dark matter. The universe is full of it. It makes up about 85% of all the mass in the cosmos. It doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation in any way we can detect. We know it exists because of its gravitational effects. Galaxies rotate faster than they should, based on their visible mass. Light bends around invisible concentrations of mass. The large-scale structure of the universe only makes sense if there's far more matter out there than we can see. But no experiment has ever directly detected a dark matter particle. The collider has searched for decades. Nothing. Then there's dark energy. The universe isn't just expanding, the expansion is accelerating. Something is pushing space apart with increasing force. The Standard Model has nothing to say about what that something is. The best estimate for the energy density of empty space, calculated from quantum field theory, differs from the observed value by a factor of 10 to the power of 120. That's not a typo. 1 followed by 120 zeros. The worst prediction in the history of physics. And then there's the matter-antimatter asymmetry. According to the Standard Model, the Big Bang should have produced equal amounts of matter and antimatter. When matter and antimatter meet, they annihilate completely, converting their mass into pure energy. If the equations were right, the universe should have destroyed itself in its first instant, everything canceling everything out. Nothing left, but something survived. You're reading this right now because matter won by a tiny fraction. The Standard Model cannot explain why. These problems have been known for decades. Physicists have built extensions, added theories, made adjustments. Nothing has filled the holes cleanly. But recently, something new has started showing up in the data, something that has the physics community genuinely nervous. It started with a particle called the kaon. Kaons are strange particles. They contain a strange quark, one of the 6 flavors of quarks that make up matter. Strange quarks were discovered in the 1950s when physicists noticed that certain particles created in cosmic ray collisions lived much longer than they should have. Something was making them hesitate. Something was slowing their breakdown. That strange behavior gave the quark its name. Kaons decay through the weak nuclear force, the same force responsible for radioactive decay. The Standard Model describes these decays with extraordinary precision, but the myths are starting to pull away from the predictions, not by much, but consistently, in the same direction, across multiple experiments. The most dramatic example comes from an experiment called NA62, which runs at the CERN facility. The team was hunting for a specific decay, a positively charged kaon breaking apart into a positively charged pion, a neutrino, and an antineutrino. The Standard Model predicts this should happen once in every 10 billion kaon decays. For comparison, your odds of winning a major national lottery are roughly 1 in 300 million. This decay is 30 times rarer than that. In 2024, the NA62 team published their result. They had captured enough events to produce a meaningful rate measurement. And the rate they measured was higher than the Standard Model's prediction. Not by a random scatter in all directions, consistently higher, in a way that points toward the same kind of deviation showing up in other experiments. Here's why this matters. The Standard Model predicts this specific decay with some of the greatest precision in all of physics. The calculation is clean because it involves a short-distance quantum interaction, meaning fewer of the messy, hard-to-calculate effects that cloud other measurements. Physicists trust this prediction more than almost any other in the entire model. So a deviation here carries more weight than a deviation somewhere harder to calculate. Think of it like a measuring tape that you've calibrated perfectly against a known standard. If that tape, after all that calibration, gives you a reading that doesn't match the object you're measuring, you take it seriously. So the tape is right. Something about the object is different from what you expected. The kaon is giving a different reading. Something is influencing its decay rate. Either a particle too heavy to show up directly in the detector is acting as a messenger behind the scenes, or an undiscovered force is nudging the process in a direction the Standard Model doesn't account for. Neither possibility fits neatly into existing physics. Both would require new physics beyond the Standard Model. And the kaon isn't alone. There are 7 specific particle interactions, 7 types of particle decay, where the evidence keeps suggesting something interfered, something that has no name in the current rulebook. The physics community calls them the Magnificent Seven. Each one involves particles containing quarks breaking apart and transforming into lighter particles in ways that the Standard Model can predict with extraordinary precision. The key word there is can, because the predictions keep failing to match the measurements. 2 of these interactions involve particles called B mesons, which contain bottom quarks. Another involves particles called D mesons, and 2 of the most sensitive involve kaons. The deviations are small, barely measurable, but they show up repeatedly across multiple experiments under conditions designed to eliminate errors. The numbers keep coming back slightly wrong in the same direction. To a physicist, that pattern means something. Random errors scatter in all directions. Systematic signals point the same way every time. The data is pointing. On the other side of the world, in a concrete building tucked inside a research campus in Tokai, Japan, a different team of physicists is running a different version of the same hunt. The experiment is called KOTO. It targets neutral kaon, the uncharged version of the same particle the Swiss team studied. Neutral kaons decay differently from charged ones. The specific process KOTO is measuring is even rarer. The Standard Model predicts it should happen roughly 3 times in every 100 billion neutral kaon decays. Why build 2 separate experiments chasing the same type of event on opposite sides of the planet? Because independent confirmation is the most powerful tool in science. History is full of signals that turned out to be noise, instrument errors that looked like discoveries, statistical flukes that vanished when more data arrived. The scientific community learned this the hard way over decades, and the response was a culture of intense skepticism toward any single result. no matter how clean it looks. If two completely independent experiments using different equipment, different kaon types, different analysis methods, and different physics teams arrive at consistent deviations from the same standard model prediction, the probability that both are wrong in the same direction by coincidence becomes vanishingly small. CODO has been running since 2013. In 2019, the team announced a preliminary result showing more events than the standard model predicted. The physics world lit up. Physicists started publishing papers exploring what kind of new particle could explain the excess. Then further analysis revealed that some of the excess could potentially be explained by background events the team hadn't fully accounted for. The excitement cooled, but the mystery didn't disappear. The hunt continued. Detector upgrades were made, analysis methods were refined, and as the NA62 team in Switzerland published their own higher-than-predicted rate in 2024, CODO's newer dataset is now being analyzed with those results in mind. The two experiments are converging on the same territory from different angles. If both land consistently above the standard model's prediction, the case for new physics becomes extremely difficult to ignore. What could cause this? Several possibilities are being seriously studied. A new heavy particle, sometimes called a leptoquark, that mediates interactions between quarks and leptons in ways the standard model doesn't include. Extensions of the Higgs sector, meaning additional Higgs-like particles that influence rare decays, or entirely new symmetries of nature operating at a scale so small that no instrument has ever directly probed it. That scale has a name. Physicists call it the zepto-universe. A zeptometer is 1/60th of a meter. If you lined up 1 billion atoms side by side, their combined width would still be incomparably large compared to 1 zeptometer. The current collider can probe down to about 50 zeptometers, which is already far smaller than anything visible to human senses. The zepto-universe sits at 10 to the power of minus 21 meters. That's roughly 20 times smaller than what the collider can currently reach. Scientists can't see it directly. No instrument built today can reach it. So why do physicists believe it exists? Because the math keeps pointing there. When researchers calculate where the gaps in the standard model are located, when they trace the origin of the anomalies showing up in the collision data, when they work backward from what the Higgs boson's mass implies, the calculations keep landing at the same address, the zeptoscale. A region of reality just below the current limit of detection, where new forces and undiscovered particles may be operating in ways that shape everything above them. This is the frontier physicists are most excited and most frustrated by simultaneously. Excited because the evidence suggests something real is there. Frustrated because reaching it directly might require a collider dozens of times more powerful than anything built today. Something the size of a city. Something that would take generations to fund and build. So instead of seeing the zepto-universe directly, researchers hunt for its shadow. Every particle interaction that happens at detectable scales sends ripples backward from whatever lies below. Like how you can know a stone landed in a lake you can't see just by watching the ripples reach the shore. If new particles or forces exist at the zeptoscale, their presence will distort the behavior of known particles in measurable ways. Finding those distortions is the entire strategy. There's a classic trick in physics. If you can't observe something directly, observe what it does to everything around it. Nobody has ever seen a black hole with a direct photograph of the object itself. What we see are the jets of material being sucked in, the distortion of light bending around the gravitational pool, the behavior of nearby stars being flung into strange orbits. The black hole announces itself through its effects on everything else. The zepto-universe works the same way. Scientists at the collider can't fire a beam at something 20 times smaller than their detectors can reach. The physics won't allow it with current technology. So instead, they designed a different kind of experiment. Rather than looking at the hidden scale directly, they study specific particle interactions at detectable scales with extreme precision. Precision so extreme that any tiny influence from below would show up as a measurable deviation in the numbers. The logic works like this. If you know exactly how a particle should behave based on every known force and every known particle in the standard model, and you then measure its actual behavior thousands of times under controlled conditions, any consistent difference between prediction and reality becomes a signal, a whisper from below. The challenge is making the measurement precise enough to hear that whisper. The collider generates millions of particle collisions every second. Most of them produce common, well-understood outcomes that physicists have mapped in exhaustive detail. But scattered across all those ordinary collisions are a handful of ultra-rare events, interactions that the standard model says should almost never happen. Events so unlikely that out of billions of collisions, only a few clean examples survive. Those rare events are the most sensitive instruments scientists have, because the rarer the process, the more a hidden influence from below can change its rate. A common event happening a billion times might shift by a few percent if something unknown nudges it. A rare event happening once in 10 billion collisions might double or triple its rate if the same unknown force pushes it. The signal is louder on the rare events, even though they're harder to catch. This is what makes the next set of experiments so important. Teams at the collider and at the separate facility in Japan are measuring the decay rates of specific particles with strange and bottom quarks with a level of precision that wasn't achievable 10 years ago. If those decay rates match the standard model's predictions exactly, it means the model is holding, at least at that scale. But if the rates come back even slightly different consistently across multiple independent measurements, it means something unknown is influencing the outcome, something from a layer of reality the detectors can't directly see. The measurements are already showing hints, small deviations, consistent directions. Scientists are careful to say they have not confirmed new physics yet. The data needs more collisions, more statistics, more independent verification. But the hints are there, and the hints connect to something even deeper, something that touches the most fundamental question in all of science. Why does anything exist at all? Let's go back to the beginning, the Big Bang. According to the standard model, the Big Bang should have created equal amounts of matter and antimatter. Every particle had an antiparticle twin, electrons and positrons, protons and antiprotons. For every piece of matter, a mirror image of equal mass and opposite charge. And when matter meets its antimatter twin, both are annihilated. They vanish in a burst of energy, completely, totally, leaving nothing behind. If the standard model is correct, the universe should have annihilated itself in the first fraction of a second after it began. Complete mutual destruction, nothing surviving, a cosmos of pure energy and emptiness. Instead, you exist. The atoms in your body are made of matter. The chair you're sitting on is made of matter. Every star and every galaxy in the observable universe is made of matter. Antimatter exists in tiny, fleeting amounts, created briefly in particle collisions and in certain radioactive decays, but immediately annihilated upon contact with any nearby matter. The universe is overwhelmingly made of one type, and physics cannot explain why. This asymmetry has a technical name: baryogenesis, the process by which matter came to dominate over antimatter in the early universe. And despite decades of work, no one has found a satisfying explanation. The standard model does include a small imbalance between how matter and antimatter behave. This imbalance is called charge parity violation. Scientists discovered the first hints of it in the 1960s by studying the decay of kaons. Different types of kaons decay at slightly different rates, depending on whether they contain matter or antimatter components. This tiny asymmetry was the first experimental evidence that matter and antimatter are not perfectly symmetric, but the asymmetry measured in the standard model is far too small, by a factor of billions. The tiny imbalance that physics currently accounts for could not have produced a universe dominated by matter. Something much larger tipped the scales, something outside the model. Physicists have been searching for additional sources of charge parity violation in other particle systems. B mesons, which contain bottom quarks, have been studied intensively at collider experiments around the world. Additional asymmetries have been found. They're real, and they're still too small to explain the universe you live in. The Magnificent Seven experiments are partly a search for this missing asymmetry. If new particles or new forces are influencing the decay rates of kaons and B mesons in ways the standard model doesn't account for, Those same new forces might carry a larger charge parity violation, large enough to explain why matter survived. The stakes here go beyond academic curiosity. The existence of stars, planets, chemistry, biology, and human consciousness is the direct consequence of matter winning over antimatter by a fraction in the first instant of time. Finding the mechanism that caused that victory would be one of the most profound answers in the history of science, and the experiments that might reveal it are already running. Now let's talk about what's actually happening inside the machine. Because the technology capturing these hints of new physics is itself one of the most extraordinary things ever built. At the moment, two proton beams collide inside the Large Hadron Collider. Something extraordinary happens. Hundreds of new particles spray outward in every direction from the collision point. They arrive at the surrounding detectors in less than a billionth of a second. Each particle leaves a distinct signature as it passes through different layers of the detector. Some are charged and curve in the magnetic field. Some deposit energy in specific ways. Some pass through certain materials and stop. Some barely interact with anything at all. A single collision lasts a fraction of a second, and the collider produces roughly 40 million collisions every second. The detectors have to capture all of it. The two largest detectors are called Atlas and CMS. They sit at opposite ends of the ring, each one surrounding a collision point and recording the aftermath. Both are built like enormous multi-layered onions, with each layer serving a specific detection function. The innermost layers track the precise paths of charged particles. The middle layers measure energy deposits. The outermost layers capture the particles that make it farthest from the collision point. The CMS detector weighs 14,000 tons. That makes it heavier than the entire Eiffel Tower. It fills a chamber the size of a 5-story building. Its central component is a massive superconducting magnet that generates a field strong enough to bend the paths of fast-moving charged particles. Without that bending, you can't measure particle momentum. And without momentum, the physics falls apart. Inside CMS are crystals made from a material called lead tungstate. They are completely transparent, like clear glass, but they are denser than iron. When a particle hits one of these crystals, the crystal flashes with light. Sensitive electronic sensors around the crystal capture that flash and convert it into a digital signal. The pattern and intensity of the flashes tell physicists what type of particle hit the crystal and how much energy it carried. The detectors photograph every collision at 40 million frames per second. The raw data from that imaging rate would be completely unmanageable. The facility generates over 90 petabytes of data every year. That's equivalent to around 20 million 4-drawer filing cabinets packed full of documents. Storing and analyzing all of it is physically impossible. So a sophisticated filtering system triggers on specific patterns in real time, selecting only the most interesting collisions to record fully, and discarding the vast majority in an instant. This filtering means there is a real possibility that some genuinely interesting events get thrown away before anyone can look at them. The filter has to make decisions in microseconds. Physicists design the filter rules carefully to preserve the rarest and most theoretically significant event types. The rare kaon decays and B meson anomalies are exactly the type of events those filters are tuned to keep. Every particle track saved, every energy deposit recorded adds to the statistical pool that determines whether the deviations from the standard model are real signals or background noise. The detectors are extraordinarily sensitive. But even at this level of precision, one aspect of the physical environment causes a headache nobody expected: the moon. The tunnel is deep underground. It is sealed from the surface. The entire machine operates in a vacuum colder than outer space, and yet twice a day the orbit of the moon changes the path of the proton beams. Not dramatically. The shift is measured in fractions of a millimeter. But fractions of a millimeter matter enormously when you're trying to steer a beam of protons traveling at 99.9% the speed of light through a tube less than 4 inches across. A tiny shift in the beam path changes where the collisions happen, which changes the geometry the detectors are calibrated to expect, which can introduce errors into the measurements. The effect is gravitational. As the moon moves through its orbit, its gravitational pull causes the Earth's crust to flex very slightly in what geologists call Earth tides. The ground the collider tunnel sits in rises and falls by a few inches twice a day as the crust responds to the moon's pull. The 27-kilometer circular tunnel deforms along with the ground. The precise circular geometry the engineers built changes shape slightly with the tidal cycle. Engineers at the facility discovered this effect during the first operations of an earlier machine in the same tunnel. They noticed that the beam required constant small adjustments at a rhythm matching the lunar orbital cycle. Once they understood the cause, they built correction systems to compensate. Today, the control systems monitor the beam position continuously and apply thousands of tiny magnetic corrections every second to keep the beam on track. Part of those corrections account for the slow tidal shift in the tunnel geometry caused by the moon overhead. The same moon that causes ocean tides on the surface is being actively corrected for in real time in a particle accelerator 100 meters underground. This is one of those details that lands differently once you sit with it. The most precise physics experiment in the history of science has to account for the gravitational influence of an object 239,000 miles away. The universe refuses to let the experiment operate in isolation. Everything connects to everything else. There are other environmental effects the engineers track and correct for. The water level in Lake Geneva, several miles away, changes seasonally, and its mass redistributes slightly, altering the gravitational field around the tunnel by a tiny but measurable amount. The passage of underground trains in the Geneva suburbs was tracked during the early years of the facility because the trains caused vibrations in the rock that could theoretically affect the beam. Particle physics at this level of precision requires the entire physical environment around the experiment to be understood and accounted for. The same precision that makes the environmental corrections necessary is the same precision that makes the measurements of kaon decays meaningful. If the machine and its environment are understood so well that the trajectory of the moon overhead is being corrected for in real time, then a deviation of a few percent in a rare particle decay rate carries real weight. The machine is accurate enough to detect a whisper from a hidden universe. It just needs enough energy to push deeper, which is exactly what makes what's happening inside the beam pipes so remarkable. A vacuum more empty than anything on the surface of the Earth, and conditions inside the collisions that recreate the first instant of the universe. The Large Hadron Collider exists in two extreme states simultaneously. The beam pipes, the tubes the protons travel through, contain one of the most perfect vacuums ever created on Earth. The pressure inside is roughly 10 times lower than the pressure on the surface of the moon. The moon has essentially no atmosphere. Its surface sits exposed to the raw vacuum of space, and the beam pipes are emptier than that. This vacuum is not just for show. A single proton traveling at nearly the speed of light has enough energy that even a collision with a stray gas molecule inside the pipe would scatter it off course. To keep billions of protons traveling in a tight, controlled beam for hours, the tube they travel through has to be as close to perfectly empty as engineering allows. Creating that vacuum requires pumping chambers along the entire length of the 27-kilometer tunnel. The system pulls out virtually every air molecule from the pipes, working continuously against the slow outgassing of the metal tube walls. Achieving and maintaining this vacuum is a continuous engineering effort that runs for the entire duration of a physics run. While the beam pipes are almost perfectly empty and extraordinarily cold, the magnets that steer the beams sit at the other extreme of temperature, minus 456 degrees Fahrenheit. This temperature, achievable only with liquid helium cooling systems, is required to keep the magnets in a superconducting state. At that temperature, the electrical resistance of the magnet coils drops to essentially zero. Current flows through the coils with no energy loss. This allows the magnets to generate a field strong enough to bend the path of protons moving at near light speed. At room temperature, generating that field would require so much electricity that it would be physically and economically impossible. So the machine sits in this strange dual state. Beam pipes emptier than the moon's surface, magnets colder than the outer planets, protons racing through this engineered cold emptiness at speeds that compress relativistic time. And then the collision. When two protons meet inside the detector, the energy concentrated at the collision point reaches nearly 10 trillion degrees Fahrenheit. 10 trillion. The core of the sun reaches about 27 million degrees. The collider's collision temperature is roughly 400,000 times hotter than that. At this temperature, matter as we normally experience it ceases to exist. Protons and neutrons dissolve. The quarks and gluons inside them form a hot, dense soup that physicists call quark-gluon plasma, a state of matter that existed in the first microseconds after the Big Bang. That soup lasts for an almost unmeasurably short time before expanding, cooling, and reforming into standard particles that fly outward into the detector. The entire process, from cold vacuum to 10 trillion degree plasma to particle spray, happens in a space smaller than an atomic nucleus and a time shorter than any clock can measure. And then the detectors record what came out. Every particle in that spray carries information, its direction, its energy, its charge. The pattern of how particles emerge from a single collision tells physicists what happened at the moment of contact. Buried in those patterns are the rare decay events that carry hints of hidden physics. There's a moment inside the collider that happens 40 million times per second and is over before the fastest thing in the universe could travel the width of a human hair. Two proton beams, each traveling in opposite directions around the 27-kilometer ring, meet at one of four crossing points. The protons are focused down to a beam width thinner than a human hair. Inside each beam, billions of protons are packed together, but they're still so small relative to each other that most pass through without hitting anything. Out of billions of near misses, a fraction of a percent actually collide. When a collision happens, the two protons don't bounce off each other like billiard balls. At these energies, they tear each other apart. The quarks and gluons inside each proton interact directly, releasing the energy of the collision in a spray of new particles. This is the moment the temperature reaches nearly 10 trillion degrees, and it happens in a space so small that comparing it to an atom is like comparing an atom to a football field. The energy released in a single proton collision is equivalent to the kinetic energy of a flying mosquito. That sounds small, a mosquito. But a mosquito's kinetic energy distributed across the mass of a single proton represents an energy density that existed in the universe only in the first microseconds after the Big Bang. Compressing a mosquito's flight energy into a subatomic space recreates the most extreme conditions the universe has ever experienced since its first instant. This is not an analogy. This is the actual physics. At that temperature and energy density, the quarks and gluons that were locked inside the two protons are no longer confined. They join a brief expanding plasma of free quarks and gluons. The quark-gluon plasma, a state of matter that predates every proton and neutron in the universe. The plasma lasts for about 10 to the power of minus 23 seconds, shorter than any other time scale in experimental physics. Then it cools. And as it cools, quarks recombine into new particles. Some of those particles are familiar. Pions, kaons, protons, neutrons. Some are heavier and more exotic, living for only a tiny fraction of a second before decaying into lighter particles. And some are the ultra-rare events the experiments are hunting for. The specific decay patterns that might carry signals of physics beyond the standard model. The detector has to capture all of this within billionths of a second of the collision happening. Every layer of the detector serves a purpose in this capture. The innermost tracking layers record the precise paths of charged particles emerging from the collision vertex. The calorimeter layers measure how much energy each particle deposits. The outer muon detectors capture the particles that travel farthest before interacting with any material. Assembling all these signals back into a picture of what happened at the collision point is an act of reverse engineering the physics of the Big Bang. One collision at a time, 40 million times per second. The data from all those collisions, stacked, filtered, analyzed, and compared to standard model predictions is what produces the hints currently making physicists nervous. And the sheer volume of that data is a challenge unlike anything in the history of computing. The collider does not just break physics records. It breaks data records too. Every year, the experiments at the facility generate over 90 petabytes of data. To put that in terms that connect to something real, a single petabyte is roughly equivalent to 10 billion photographs on a smartphone. 90 petabytes is 900 billion photographs. Stacked as printed photos, that pile would reach from Earth to the moon and back several times over. And this is the data that survives the filter. The raw output before any selection would be orders of magnitude larger. The filtering system, called the trigger, is a real-time decision engine running at the speed of the physics itself. At the moment a collision happens, the trigger has roughly 1 microsecond to assess the initial detector signals, decide whether the event is interesting enough to save, and either record it or discard it permanently. Most events get discarded. The machine is designed to do this because saving everything would require a data pipeline too large to exist with current technology. The trigger is programmed to look for signatures that match theoretically important events. A specific pattern of particle tracks, an unusual energy distribution, a missing momentum signature that might indicate a particle escaped without interacting. Rare kaon decay patterns are on the trigger list. This creates a philosophical tension that physicists openly discuss. If something genuinely new shows up in the data but doesn't match any pattern the trigger was programmed to look for, the event gets deleted before anyone ever sees it. The trigger is designed based on current theories. It is, at some level, looking for what physicists already expect to find, with variations. Something completely outside the theoretical framework might be systematically discarded by a filter that doesn't know to look for it. Researchers are aware of this problem and work to build as broad a trigger strategy as possible. But the fundamental constraint remains. You can't save everything. The 90 petabytes that do get saved flow into a computing grid spanning dozens of universities and research centers across the world. The facility operates one of the largest distributed computing networks ever built. Data from the collision hall in Switzerland arrives at computing centers in the United States, the United Kingdom, France, Germany, and elsewhere within seconds. Physicists at institutions worldwide analyze pieces of the data set simultaneously. This distributed system allows the data volume to be processed, but it also introduces coordination challenges. Keeping analysis consistent across dozens of sites requires constant cross-checks. Systematic errors in one computing center's analysis need to be identified and corrected before they contaminate the global result. After all this filtering, transmission, storage, and analysis, the final output for a year of running might be a handful of numbers. Branching ratios, cross-sections, angular distributions, small tables of measurements with error bars attached. Those numbers are compared to the standard model's predictions. And right now, some of those numbers don't match. The deviations aren't large enough yet to declare a discovery, but they're consistent enough, and they're pointing in a direction that, if confirmed, would require adding something fundamental to humanity's understanding of the universe. What that something is, nobody is sure. But one possibility being studied is so extreme that some physicists hesitate to say it in public. The possibility that the ground floor of reality itself is unstable. The universe feels stable. Stars burn for billions of years. Atoms hold together across geological timescales. The laws of physics appear consistent whether you measure them here on Earth or observe them in light, arriving from galaxies 12 billion light years away. Everything around you suggests a cosmos built on a solid foundation. But there is a calculation physicists keep running, based on the confirmed mass of the Higgs boson and the measured mass of the top quark, and it produces a result that is deeply uncomfortable to sit with. The calculation is about the energy state of the vacuum of space itself. In quantum physics, the vacuum is not empty. It is a seething field of energy, with particles constantly blinking in and out of existence and fields permeating all of space. Every field has an energy state, and the lowest possible energy state a field can occupy is called its true vacuum. A field not sitting at its true vacuum is sitting at a higher energy called a false vacuum. The field appears stable, can stay that way for an enormous length of time, but is always technically at risk of tunneling down to a lower energy state through a quantum process. Run the numbers using the Higgs boson's confirmed mass of about 125 giga-electron volts, combined with the best current measurements of the top quark's mass, and the equations land in a zone physicists call metastable. The Higgs field may be sitting in a false vacuum, not at the absolute lowest energy it could occupy, sitting on a shelf above the true bottom, held in place by the shape of the energy landscape, but with a small, non-zero probability of quantum tunneling downward. Think of a ball resting in a shallow bowl carved partway up a hill. It's stable in that bowl. It can sit there for billions of years. But the bowl has a wall, and if the ball crosses the wall, it rolls down to the actual valley floor below. The ball doesn't need to be pushed over the wall. In quantum mechanics, it can tunnel through. The universe may be that ball. Physicists are quick to stress several things, like, first, the time scale for any such tunneling event, if the metastable interpretation is correct, is likely to be vastly longer than the current age of the universe, potentially trillions upon trillions of years. Second, the calculation depends sensitively on the exact masses of the Higgs boson and the top quark, both of which have error bars that currently straddle the boundary between stability and metastability. Improve the measurements and the answer might shift. The universe might turn out to be fully stable, but it might not. And the unsettling part is not the time scale. It is the mechanism. If a quantum tunneling event did occur, it would happen without any warning. There would be no signal, no observable precursor. A bubble of true vacuum would nucleate at a point in space and expand outward at the speed of light. The bubble wall would carry with it a region where the laws of physics are fundamentally different, where the strengths of forces, the masses of particles, and the rules governing chemistry and biology are all different from everything inside. Everything the bubble wall touched would be converted instantly. You would not see it coming. Light from the approaching wall couldn't outrun the wall. Physicists studying this possibility are not panicking, but they are measuring the Higgs mass and the top quark mass with increasing precision. Because right now, the fate of the universe, according to the equations, depends on exactly where those numbers land. And the machine doing the measuring is about to get a significant upgrade. Picture the most dramatic explosion you can imagine. A nuclear weapon, a volcano, a gamma ray burst from a dying star, millions of light years away. Every one of those events, as violent as they are, leaves the underlying laws of physics completely intact. Matter gets rearranged, energy gets released. But the rules governing atoms, the speed of light, the strength of gravity remain unchanged throughout. A vacuum collapse would be different in kind, not just in scale. If the Higgs field tunneled from its current metastable state down to the true vacuum, the physics inside the expanding bubble would be governed by a completely different set of constants. The masses of particles would change. The strength of the electromagnetic force would shift. The balance between forces that allows atoms to form, that allows stars to burn, that allows chemistry to produce molecules, would all be different from anything in the universe we inhabit. Matter as it currently exists would cease to be viable. The bubble would expand outward from its origin point at the speed of light. This speed is important. It means the bubble can never be observed before it arrives. If the tunneling event happened in a galaxy 1 million light years away right now, the bubble front would reach Earth in 1 million years, traveling at light speed, invisible in front of it. You can't see something moving toward you at the speed that carries all information. The transition, when it arrived, would be instantaneous from any observer's perspective. One moment standard physics, the next a universe with different rules. Physicists sometimes describe this as the ultimate cosmic reset. The bubble doesn't destroy the universe in the way a bomb destroys a building. It converts it, replaces the current physical laws with a different set, building an entirely different kind of universe behind it, one that operates by entirely foreign rules, and almost certainly can't support anything resembling the structures that exist in ours. Now, before this image takes hold too firmly, several important things are worth placing alongside it. The scenario assumes the universe is genuinely in a metastable state, and that remains an open question. Current measurements of the Higgs mass sit close to the boundary between stable and metastable. Refining those measurements is an active priority at the facility. If the true mass turns out to be slightly higher than current central estimates, the stability calculation could shift to a fully stable result. There is also the question of whether the collider itself could trigger such an event. This has been studied carefully. The answer, based on the physics, is clearly no. The energy densities at the collider, while extreme by any human standard, are dwarfed by the energies of cosmic ray collisions that bombard Earth and every other object in the universe continuously. If collider scale energies could trigger a vacuum collapse, cosmic rays would have triggered one long ago. The universe's age is evidence that the events happening at the facility are well within the safe zone. The measurement program continues: Higgs mass, top quark mass, precision decay experiments. Each measurement tightens the constraints on the stability calculation, but the outcome isn't confirmed yet. And the thing that determines the outcome most precisely is a number that was already found. A number with mass. One number, one measurement. The fate of the universe's stability sitting on its decimal places. When physicists confirmed the Higgs boson in 2012, the immediate celebration was about completing the Standard Model's roster of particles. The Higgs was the last predicted piece. Finding it felt like closing a chapter. What the physics community didn't emphasize loudly in the public celebration was what the specific mass implied: 125 gigaelectron volts. That number placed the Higgs boson right at the edge of a stability cliff. Here's the picture. Imagine a stability chart where the horizontal axis is the Higgs boson mass and the vertical axis is the top quark mass. The chart has three regions: a fully stable zone, a fully unstable zone, and a metastable zone in between. Fully stable means the Higgs field sits in an absolute energy minimum and stays there forever. Fully unstable means the field would have already collapsed long ago. The universe wouldn't exist if it were there. Metastable means the field is in a local minimum that looks stable but isn't the deepest possible state. It can last an enormously long time, but given infinite time or given a sufficiently energetic quantum fluctuation, it collapses. The measured values of the Higgs boson mass and the top quark mass currently place our universe in the metastable region, close to the boundary with fully stable, but inside the metastable zone according to the best current measurements. The closeness to the boundary is actually interesting to physicists for a different reason. Sitting near the edge of stability could itself be a clue. Some physicists think this near criticality is connected to deeper physics at very high energies. The suggestion is that additional interactions, perhaps the kind occurring in the Zepto universe, stabilize the Higgs field in a precise way that happens to land the mass very close to the edge of stability. If that's right, the metastability is a feature, not a danger signal, a sign that something deeper is at work. Improving the Higgs mass measurement is therefore valuable in two ways. It either shifts the stability calculation toward the safe zone, reducing the theoretical concern, or it confirms the metastable picture more precisely, giving physicists stronger constraints on what kind of new physics would be needed to stabilize it. The high luminosity upgrade of the collider will produce millions of Higgs bosons, where the current machine produces thousands. That flood of new data allows the mass to be pinned down to a precision that isn't currently achievable. Small refinements in the mass measurement could move the universe's position on the stability chart in ways that change the theoretical picture significantly. 1 decimal place on a particle's mass, measured 100 meters underground, they're potentially revealing whether the ground floor of physics is solid or hollow. The precision required for that measurement demands far more collisions than the current machine can produce, which is why starting in 2026, the collider is going quiet. In 2026, they switch it off. The proton beams stop. The cryogenic cooling systems are partially warmed. Thousands of engineers and technicians descend into the 27-kilometer tunnel, carrying equipment, tools, and years' worth of maintenance plans. The world's most powerful particle accelerator enters its longest planned shutdown since the beginning of operations. Long Shutdown 3 is not a pause. It is a transformation. The goal is to prepare the facility for its most ambitious upgrade yet. Every component that limits the number of collisions the machine can produce needs to be either replaced or modified. Magnets near the 4 collision points will be swapped out for a new generation of superconducting magnets built with technology that didn't exist when the original machine was commissioned. These new magnets are stronger. Stronger magnets focus the proton beams more tightly. A tighter beam means more protons pass through the same microscopic collision zone per second, which means more collisions. The inner detectors at the largest experiments are also being rebuilt. The innermost tracking layers take enormous punishment from the intense radiation produced by millions of collisions per second. After years of running, radiation damage degrades their precision. The upgrade replaces them with new silicon tracking detectors capable of operating at the higher collision rates the upgraded machine will produce. New electronics throughout both large detectors will also be installed. The trigger systems that decide in microseconds which events to save need to be upgraded to handle a data rate 10 times higher than what the current systems process. This requires custom-designed chips capable of faster processing, running algorithms more sophisticated than anything deployed in the existing detectors. The shutdown is scheduled to last until approximately 2029, 3 years of construction inside a tunnel that requires specialized training just to enter. Teams from dozens of countries coordinate through a project management structure designed to keep thousands of parallel tasks moving without collision. During this period, no new physics data comes from the main experiments. The scientific community shifts its focus toward analyzing the enormous data sets already collected and publishing results from years of previous runs. Papers continue to emerge. Anomalies get studied with more sophisticated analysis tools. The kaon decay results and the hints in the B meson sector get scrutinized by theorists building models of what might explain them. The physics community uses the shutdown productively, but there is a quiet urgency underneath the activity. Because the shutdown is preparation for something that physicists believe could finally push the measurements past the threshold that current data can't cross. The upgraded machine will be capable of generating 10 times more collisions every second than the current version. 10 times more collisions means 10 times more rare events. 10 times more kaon decays, 10 times more Higgs bosons, 10 times more chances to catch the signal that the current data set is only hinting at. If the deviations seen so far are real, the upgraded machine will confirm them with enough certainty to officially break the standard model. If they vanish with more data, it tells physicists something equally important. The anomalies were statistical noise, and the search needs to go somewhere else. Either outcome changes physics, but the outcome that physicists are most quietly hoping for, the one that would reshape everything, requires the upgraded machine to catch something no detector has ever caught before. Luminosity is the word physicists use for collision rate. A high luminosity machine is one that produces an enormous number of collisions per unit time. And the upgrade coming after Long Shutdown 3 will make the current collider look, by comparison, like a first draft. The High Luminosity Large Hadron Collider is scheduled to begin data collection around 2029. When it does, the collision rate will be 10 times higher than the original machine's design peak. Billions of collisions every second, sustained over years of running. The physics case for this increase is direct. Every rare process the facility studies improves in statistical precision as the number of observed events grows. A signal showing up at 2 standard deviations of significance in the current dataset, close to interesting, but short of compelling, becomes 5 standard deviations in the upgraded data. If the deviation is real, 5 standard deviations is the threshold particle physics uses for an official discovery claim. It means the probability of the result being a random fluctuation is less than 1 in 3 million. The kaon anomaly from the NA62 experiment, the B meson rate deviations, the Higgs mass measurements sitting near the stability boundary. Every one of these gets pushed across or firmly away from the discovery threshold once the upgraded machine runs at full luminosity for several years. But the upgrade isn't just about measuring known hints more precisely. It's about reaching into regions of physics currently invisible. The collider's detectors have a dark zone. regions of parameter space where the signals of new particles would be too rare or too subtle for the current machine to collect enough examples. The standard model extensions that theorists have built to explain dark matter, or the matter-antimatter imbalance, or the kaon anomalies, all predict additional particles and interactions. Many of those predictions place the new particles in mass ranges the current machine can produce, but can't study with sufficient statistics. The high luminosity upgrade pushes those regions into full view. A particle that might appear once in every 10 billion collisions at the current machine becomes observable in a statistically meaningful sample after years of running at 10 times the collision rate. The magnets driving this upgrade are a significant engineering achievement on their own. The new focusing magnets near the collision points use a niobium tin alloy that can carry higher electrical currents than the niobium titanium magnets used in the original machine. Higher current means stronger magnetic field. Stronger field means tighter beam focus. Tighter focus means more protons overlapping in the same collision region per second. Niobium tin is harder to manufacture and more brittle than the original magnet material. Bending it into the precise coil shapes required for focusing magnets required new fabrication techniques developed specifically for this upgrade. Hundreds of these magnets have been built at facilities across the world and will be installed during the shutdown. When the machine restarts, the physics community will have access to a data stream that is categorically different from anything collected before. And several of the first targets on the physics list touch directly on the zones of the universe that the current experiments can barely see at the edge of their sensitivity, the dark sectors. There are parts of the universe the current detectors can feel but not see. Physicists call them dark sectors. The phrase covers a collection of theoretical ideas about physics that operates outside the known particles and forces of the standard model, but at energy scales, the collider can actually reach. The term dark here doesn't necessarily mean darkness in the visual sense. It means hidden, decoupled, interacting with normal matter so weakly that the interaction barely registers. The search for dark sectors looks different from the search for the Higgs boson or a standard heavy particle. Those particles decay quickly into well-known final states that light up the detector in clear patterns. Dark sector particles, if they exist, might travel significant distances before decaying, or decay into combinations of particles that are harder to distinguish from background processes. They might produce displaced decay vertices, meaning the decay happens not at the collision point, but at a measurable distance away inside the detector. The facility has several specialized experiments designed for exactly this type of search. One of them, called Phaser, sits in a narrow tunnel more than 1,500 feet away from the main collision point. The experiment is designed to catch particles so weakly interacting that they travel the entire length of the tunnel and only decay inside the small detector at the far end. Catching even a handful of these events would be evidence of physics operating in the dark sector. Another experiment, called the scattering and neutrino detector, looks for neutrinos produced in the collision zone that then interact in a dense tungsten block farther along. Neutrinos are the classic dark sector particle, in the sense that they interact with normal matter so feebly that trillions of them pass through your entire body every second without touching a single atom. Measuring neutrinos produced directly at the collision point allows physicists to test whether neutrino behavior matches expectations or shows signs of additional mixing with hypothetical heavier partners. These heavier neutrino partners, sometimes called sterile neutrinos, are one of the most promising candidates for both dark matter and for the extra charge parity violation needed to explain the matter-antimatter imbalance. If sterile neutrinos exist and mix with regular neutrinos in measurable ways, their influence would show up as subtle deviations in neutrino detection rates across different experiments. The current collider has placed limits on where these particles can be hiding. It has ruled out large regions of the parameter space where theorists initially expected to find them, but it hasn't ruled out the full territory. The high luminosity upgrade extends the search into the regions current data can barely probe. Dark sectors represent the possibility that the universe has entire categories of particle and force that are real, physically present, influencing matter and gravity, but essentially transparent to everything we've built to detect them. The matter you're made of, the light that lets you see, the forces that hold atoms together, might all exist in a small, bright corner of a much larger physics. And the edge of that larger physics might be visible, just barely, to an experiment running right now on the collider floor. Every second, approximately 100 trillion neutrinos from the sun pass through your body. 100 trillion, every single second. They enter from above, pass through your skin, your organs, your bones, and exit through the ground below you. Your body is essentially transparent to them. So is the Earth. A neutrino, traveling at nearly the speed of light, can pass through a block of lead 1 light year thick and have roughly even odds of interacting with a single atom. This near-complete invisibility makes neutrinos one of the most maddening particles in physics. They were theorized in 1930 by physicist Wolfgang Pauli, who proposed their existence to explain why energy seemed to go missing in certain radioactive decays. He predicted a particle so undetectable he initially believed it could never be confirmed experimentally. He almost apologized for proposing it. Neutrinos were experimentally confirmed 26 years later using a detector placed near a nuclear reactor where the flux of neutrinos was high enough that occasional interactions became measurable. Since then, physicists have learned a great deal about neutrinos. They come in 3 varieties called flavors: electron neutrinos, muon neutrinos, tau neutrinos, and as neutrinos travel, they oscillate between these flavors. An electron neutrino produced at the sun's core might arrive at Earth, partly converted to a muon neutrino. This oscillation is confirmed and was awarded the Nobel Prize. The oscillation itself is remarkable because it proves something the Standard Model originally assumed to be false. Neutrinos have mass. The original version of the Standard Model assigned neutrinos 0 mass. The observation of flavor oscillation requires mass, and so the Standard Model had to be extended. This extension is the source of deep theoretical discomfort. The mass of neutrinos, while confirmed to exist, is extraordinarily small. Millions of times lighter than the electron, which is already the lightest known massive particle. No theoretical mechanism in the Standard Model naturally produces such a small mass without what physicists consider a severe fine-tuning problem. The leading explanation for why neutrino masses are so tiny is a mechanism called the seesaw mechanism. The idea is that the neutrinos we observe are light because they're partnered with an extremely heavy version, a sterile neutrino, and the 2 masses balance each other mathematically. The heavier the sterile neutrino, the lighter the observable one. If sterile neutrinos exist and are in the right mass range, the collider can search for them. They would be produced occasionally in high-energy collisions and would travel invisibly through the detector. But their existence would manifest as missing energy, and their eventual rare decays, if they happen inside the detector, would produce distinctive signatures. Finding sterile neutrinos would simultaneously explain the lightness of observable neutrinos and potentially provide the additional charge parity violation needed to explain why matter survived the Big Bang. 2 of the biggest mysteries in physics, one proposed particle that might connect them both. The search continues, and the stakes underneath it are higher than almost anything else the facility is chasing. Running the most complex machine ever built costs roughly the same as powering a small city for an entire year. The facility uses approximately 1.3 terawatt hours of electricity annually. That number sits alongside cities of around 300,000 people. During peak physics runs, the power demand spikes higher, and the facility works with regional energy providers to manage the draw against the grid. This consumption isn't waste. Almost every component of the machine either requires enormous power to operate or requires enormous power to keep cool. The superconducting magnets need continuous refrigeration to stay at minus 456 degrees Fahrenheit. The cryogenic systems running that refrigeration are themselves massive engineering structures. The radio frequency cavities that accelerate the proton beams use high-power radio waves to push the protons forward on every loop around the ring. The computing grid processing 90 petabytes of data annually runs continuously across dozens of sites worldwide. The facility is aware of its energy footprint. Engineers have pursued efficiency improvements in the cryogenic systems, the computing infrastructure, and the accelerator systems over successive operational years. The high luminosity upgrade includes provisions for more energy-efficient magnet cooling designs. But the fundamental physics of what the machine does, generating the highest energy particle collisions ever achieved by human technology, requires energy. There is no low-power shortcut to the Zepto universe. The antimatter produced at the facility illustrates the energy cost of this physics in a different way. The facility produces small quantities of antihydrogen and other antimatter particles as byproducts of certain experiments. If you collected every single antiparticle ever created at the facility across its entire operational history, every antiproton, every positron, every antihydrogen atom, and annihilated them all simultaneously with matter, the total energy released would be insufficient to power a single light bulb for even a short time. This is the scale at which physics operates when it's probing the fundamental structure of matter. The experiments are extraordinarily sensitive. The signals being hunted are microscopic, but the machine required to reach those signals is enormous, expensive, and power-hungry. And the components that make the measurements themselves are physically remarkable. Inside the detectors sit materials that seem to violate common intuition just by existing. The lead tungstate crystals at the heart of the electromagnetic calorimeter inside the CMS detector are completely transparent to visible light. You could hold one up and look through it like glass, but the same crystal is roughly 8.5 times denser than water and significantly heavier than solid iron. Thousands of these crystals, each about the size and shape of a thick marker, pack into the calorimeter structure and flash with tiny bursts of blue and ultraviolet light whenever a particle deposits energy inside them. Every flash is digitized, every pattern of flashes reconstructed into a particle track, every track folded into the statistical analysis, hunting for deviations from the standard model. And those deviations, when they show up, arrive in the form of numbers. Numbers that the physics community then debates fiercely, because the difference between a real signal and a statistical fluctuation can be a matter of a fraction of a percentage point. That debate is one of the most productive and contentious conversations in modern science. Particle physics has a word for getting it wrong in a visible way. It's called a 3 sigma result. In statistics, sigma measures how far a result sits from the expected baseline in units of standard deviation. A 1 sigma deviation happens about 30% of the time by pure chance, even with no real signal present. A 2 sigma result is a bit unusual. A 3 sigma result, meaning the measurement sits 3 standard deviations away from the prediction, happens roughly once in every 300 measurements by chance. 3 sigma results have a history in particle physics of generating excitement and then disappearing. In the early 2000s, several experiments reported 3 sigma hints of new particles that vanished when more data arrived. In 2015, an excess appeared in the Large Hadron Collider data, suggesting a possible new particle at a specific mass. Papers flooded the physics community, exploring theoretical explanations. Several hundred papers were written in the months following the result. The excess disappeared entirely in the next dataset. The particle didn't exist. This history makes physicists extremely cautious about any result below 5 sigma, 5 standard deviations of significance. The probability of a 5 sigma result occurring by random fluctuation is less than 1 in 3 million. The threshold is deliberately high because the cost of a false discovery, years of theoretical work chasing something that doesn't exist, is enormous. The current anomalies in kaon decays and B meson rates sit in a range that particle physicists treat seriously, but not yet as confirmed. The Na62 kaon result and several B meson measurements from a dedicated flavor physics experiment are showing consistent deviations in the same direction across multiple channels. This consistency across independent measurements is the most persuasive feature of the current situation. A random fluctuation in one experiment is unsurprising. The same fluctuation appearing in the same direction in 5 different measurements of different particles run by different teams using different methods is substantially harder to dismiss. Theorists are divided. Some argue the pattern is compelling enough to take seriously as a signal of new physics and have built detailed models of what particles or forces could explain the combined picture. Others argue that the individual measurements, while each interesting, don't yet individually clear the bar required for confidence, and that the apparent pattern could still dissolve with more data. Both camps agree on what resolves the question. More statistics. The high luminosity upgrade provides exactly that. If the combined significance of the B meson and kaon anomalies passes 5 sigma after several years of running at 10 times the current collision rate, the standard model is officially broken. New physics is confirmed. The field restructures around the discovery. If the anomalies fade toward the prediction as statistics improve, the current hints were noise, and the search continues in a different direction. Either result is scientifically valuable. The worst outcome in physics is ambiguity, and the upgrade eliminates ambiguity by sheer statistical force. But physicists are already thinking past the question of whether the standard model breaks. They're thinking about what happens after it does. The standard model has been stressed before. In the 1970s, the electroweak theory that unified electromagnetism and the weak nuclear force was confirmed. It required extending the existing framework. In the 1980s, evidence for 3 generations of quarks forced the model to accommodate more structure than originally expected. Each time new data demanded something new, physicists absorbed it by adding to the framework. The anomalies building now feel different to many researchers. The combination of unexplained dark matter, the matter-antimatter imbalance, the neutrino mass problem, the Higgs stability question, and the rare decay deviations all pointing in the same direction suggests the current framework is missing something structural. The pattern of problems looks less like a gap to fill and more like a sign that the entire organizing principle needs revision. What would that revision look like? Several serious theoretical frameworks exist. Supersymmetry proposes that every known particle has a heavier partner particle, related by a symmetry between matter and force. These partners would solve the Higgs stability problem, provide dark matter candidates, and generate additional charge parity violation. The Large Hadron Collider has searched for supersymmetric particles across a wide mass range and found nothing yet. The absence has killed the simplest versions of the theory, but left more complex versions alive. Composite Higgs models propose that the Higgs boson is not a fundamental particle, but it is itself built from smaller constituents bound together by a new, undiscovered force. This structure naturally explains why the Higgs mass sits where it does, and predicts new resonances at energies the high luminosity machine can probe. Extra dimensions of space, proposed in several theoretical frameworks, would change how gravity and other forces behave at short distances and could explain why gravity is so much weaker than the other forces. Some extra dimension models predict the appearance of towers of heavier partner particles for known particles, called Kaluza-Klein modes, at mass scales potentially accessible to the upgraded machine. None of these frameworks has been confirmed. Each makes specific predictions that the upgraded machine will test with unprecedented precision. The experience of the last 15 years of collider data has taught physicists humility. Many theorists expected the original collider to find supersymmetric particles almost immediately. The absence forced a significant recalibration of theoretical expectations. The new models coming from this period tend to be more careful, more flexible, more focused on observable consequences rather than elegant theoretical aesthetics. Whatever the correct theory beyond the standard model turns out to be, it has to explain why the standard model works so well at currently tested scales while failing at the deepest scales. That's an extremely tight constraint. Most theories that technically extend the standard model fail this constraint by predicting effects that should have already shown up in existing data. The theory that passes this constraint, if it exists, will be one of the great intellectual achievements in the history of science. And the machine currently being prepared for its biggest upgrade yet is the instrument most likely to find the first solid sign of what that theory needs to contain. The universe has four known forces. Gravity holds planets in orbit and pulls you to the ground. Electromagnetism carries light, drives chemistry, and makes every electrical device work. The strong nuclear force locks quarks together inside protons and neutrons with an intensity that makes it the most powerful force in the known universe at short range. The weak nuclear force drives certain types of radioactive decay and played a central role in the nuclear reactions of the early universe. Four forces, described by the Standard Model plus general relativity for gravity. That framework accounts for every physical phenomenon ever directly observed by human instruments. Physicists have strong reasons to think there are more. The theoretical problem with just four forces is that gravity is wildly weaker than the others. Hold a paperclip. A refrigerator magnet can lift it off the table, overcoming the gravitational pull of the entire Earth on a tiny piece of metal. Gravity operates across cosmic distances and organizes galaxies. But at the particle scale, it is negligibly faint compared to electromagnetism or the nuclear forces. This enormous gap between gravity's strength and the others is called the hierarchy problem. The hierarchy problem suggests either that something is fine-tuned to an absurd degree in the fundamental equations, or that additional physics exists which connects the different scales and explains why gravity appears so weak. Many of the theoretical extensions of the Standard Model were built specifically to address this problem. Supersymmetry does it one way. Extra dimensions do it another. Composite Higgs models take a different approach. Each proposed solution predicts specific observable consequences. New particles at specific mass ranges, new interactions between known particles, modified rates for specific processes. The collider tests these predictions directly. But some researchers are now exploring possibilities that go beyond adding particles to the existing framework. They're asking whether the forces themselves might be different from what we think at the very smallest scales. Whether the way the four forces unify or fail to unify might reveal a deeper structure. Grand unified theories attempt to show that the strong force, the weak force, and electromagnetism are all expressions of a single underlying force that operated as one in the very early universe and split apart as the universe cooled. These theories predict that protons, which the Standard Model considers perfectly stable, should actually decay, but with an extraordinarily long half-life. Experiments searching for proton decay have run for decades without finding it. This places tight limits on many grand unified theories. A theory that successfully unifies all four forces, including gravity, into a single framework is sometimes called a theory of everything. No such theory exists in confirmed form. String theory is the most developed attempt, but it currently makes predictions at energy scales far beyond any conceivable collider. The high luminosity era won't reach a theory of everything, but it will push into energy and precision ranges where the first signs of unification or new forces might appear. A single confirmed anomaly passing the 5 sigma threshold would give theorists a real target to aim for, instead of a vast open landscape. And one of the specific targets sitting at the intersection of almost every open question in physics is this particle that most physicists believe must exist but that no experiment has ever captured. Dark matter has to be something. Physicists sometimes say this with a tone of exasperation, because the evidence for dark matter's existence is overwhelming, yet every direct detection attempt has come back empty. The particle, if it is a particle, is there. The gravitational evidence is unambiguous, but it refuses to appear in any detector. The leading candidate for decades was a class of particles called weakly interacting massive particles. The theoretical appeal of these particles was strong. If you extended the Standard Model in certain natural ways, particularly through supersymmetry, you automatically got a new heavy particle that interacted only through the weak force and gravity. This particle would be stable, invisible to light, produced in the right quantities in the early universe, and present in the right amounts to explain the dark matter observations. The pieces fit almost too cleanly. Experiments went looking. Underground detectors filled with liquid xenon, designed to catch the rare occasion when a dark matter particle bounced off an atomic nucleus, ran for years. Nothing. Larger detectors ran for longer. Still nothing. The collider searched for missing energy signatures that would indicate dark matter particles created in collisions and then escaping the detector invisibly. Nothing. The absence of weakly interacting massive particles in detector after detector, including the Large Hadron Collider across 2 full-run periods, has pushed physicists to take seriously the alternatives they previously treated as less elegant. Axions are one alternative. Originally proposed to solve a different problem in quantum chromodynamics, the theory of the strong force. Axions are extremely light particles that would interact with photons in the presence of a strong magnetic field, converting briefly into detectable light. Several experiments worldwide are hunting for this conversion. Some have recently placed the tightest constraints yet on where axion dark matter could be hiding. The search continues. Primordial black holes are another alternative. If conditions in the very early universe produced a large population of tiny black holes before any stars formed, those black holes could provide the missing mass without being particles at all. Observations of gravitational microlensing events and gravitational wave detections are being used to constrain how much of the dark matter could be in this form. None of these candidates is confirmed. Each has theoretical appeal and experimental programs pursuing it. The High Luminosity Collider will probe weakly interacting massive particle parameter space more deeply than ever before. If the particle exists in the mass ranges still allowed by current limits, a decade of running at 10 times the current collision rate should either find it or push it into regions so exotic that most theoretical motivations for the particle would disappear. That outcome, a definitive non-detection across the entire theoretically motivated mass range, would be one of the most important negative results in physics history. It would kill the most popular explanation for dark matter and force the community to fundamentally reconsider what the invisible majority of the universe is made of. Whatever dark matter is, it's out there, surrounding every galaxy, passing through the Earth continuously. And the answer to what it actually is will reshape physics completely. The only thing standing between us and that answer is precision and time. There is a number that appears in the Standard Model and has no explanation. Physicists call it the cosmological constant. Einstein introduced it first as a term in his equations for general relativity to keep the universe from collapsing under its own gravity. He later called it his greatest blunder when observations revealed the universe was actually expanding. But then in 1998, 2 independent teams measuring the distance and speed of distant supernovae discovered something that changed everything. The universe is expanding, and the expansion is accelerating. Something is pushing space apart with increasing force. The cosmological constant came back, not as Einstein's blunder, but as the mathematical description of something physically real. Physicists now call this accelerating expansion dark energy, and the cosmological constant is their best mathematical handle on it. The problem is the number. Quantum field theory, the framework underlying the Standard Model, predicts a value for the energy density of empty space based on the quantum fluctuations of all the fields that fill it. When physicists calculate this predicted value and compare it to the observed cosmological constant, the two numbers disagree by a factor of 10 to the power of 120. That is not a typo. 1 followed by 120 zeros, the worst prediction in the history of physics, by an almost inconceivable margin. Something is canceling the enormous predicted vacuum energy down to the tiny observed value with extraordinary precision. A cancellation of 120 orders of magnitude requires a mechanism. The Standard Model provides no mechanism. This failure has been known for decades. Physicists call it the cosmological constant problem, and it remains completely unsolved. Some researchers believe the solution involves a symmetry that sets the vacuum energy to exactly 0, with a small additional contribution from something else providing the observed dark energy. Others invoke the anthropic principle, arguing that we observe the value we observe because only universes with small cosmological constants can form galaxies and stars, and observers. Neither answer is satisfying to most physicists. The first requires discovering a symmetry that no current theory contains. The second is philosophically uncomfortable and resists experimental testing. The collider cannot directly measure the cosmological constant, but the new physics it's hunting for Whatever explains the kaon anomalies or dark matter or the Higgs stability might connect to the mechanism that controls the vacuum energy. Theories that address the Higgs hierarchy problem often have implications for the cosmological constant problem as well. The two problems may not be separate. They may be two symptoms of the same missing piece. And the physics community's growing willingness to discuss both together reflects a broader shift. The sense that the collection of open questions has grown large enough that a single deeper explanation connecting all of them is more likely than a series of independent patches. That deeper explanation, if it exists, is waiting just beyond the current reach of every instrument ever built. Physics discoveries don't arrive with explosions. The Higgs boson discovery in 2012 was announced in a crowded auditorium with a slideshow. The result was a set of data points on a graph, a bump in a plot of particle collision rates at a specific energy, rising above the expected background with enough statistical significance to cross the 5 sigma threshold. The bump was the particle. The celebration was enormous. The graph itself looked unremarkable to anyone who wasn't a physicist. A future discovery of new physics beyond the standard model will look similar. A deviation in a measurement of kaon decay rates crossing from 2 sigma to 3 sigma to 4 sigma to 5 sigma as data accumulates over years. Or a new resonance appearing in the collision products at a mass no known particle occupies. Or a systematic missing energy signal that grows more significant with every additional run period. The process is slow, deliberate, layered with cross-checks. When a potential signal appears, the team that found it doesn't immediately go public. Internal reviews begin. Independent sub-teams within the same experiment reanalyze the data using different methods. Systematic uncertainties are stress-tested. Every known source of background is re-examined to make sure the signal isn't an artifact of how the data was processed. If the signal survives internal review, a paper is prepared and submitted to a journal. Other experiments running similar analyses are asked to check their data for the same signal. The peer review process begins. Outside, theorists start building models to explain the signal if it's real. The wider physics community discusses the result in conference talks and workshop papers. Only after independent confirmation from a second experiment, or after the same experiment accumulates enough data to push the significance past 5 sigma beyond any reasonable doubt, does the result cross the threshold into accepted discovery. This process protects physics from false discoveries. It's slow and sometimes frustrating, but it's also why the discoveries that do clear the bar are extraordinarily reliable. A confirmed discovery of new physics at the collider would cascade through the entire scientific world. Every theorist who has built a model predicting something in that region would immediately check whether their model fits the new data. Those whose models fit survive. Those whose models don't are revised or abandoned. The winning model or family of models becomes the new target for experimental tests. Experiments at other facilities worldwide would be redesigned to probe the implications of the discovery. Funding for new instruments would accelerate. The question physics has been building toward for decades, what lies beyond the standard model, would finally have an empirical foothold. And the answer to that question opens a set of further questions that physicists are already writing down, waiting for the day they have a discovery to anchor them to reality. There is a question that sits quietly at the edge of every major unsolved problem in physics. Is the standard model the kind of theory that can be fixed by adding pieces? Or is it the kind of theory that is fundamentally the wrong kind of story about reality? The history of science has examples of both. Sometimes a theory is mostly right and just needs extension. Newton's gravity was mostly right. Einstein's general relativity extended it to cover cases Newton didn't handle. High speeds, strong gravitational fields, the large-scale structure of the universe. But Newton's equations didn't disappear. They remain accurate and useful within their domain. General relativity contains Newton's gravity as a special case at low energies. Other times, a theory is wrong at a deeper level. The idea that Earth sat at the center of the solar system wasn't fixed by adding epicycles to the planetary orbits. Even though adding epicycles improved the predictions temporarily, the organizing principle was wrong. Replacing it with a sun-centered solar system wasn't an extension. It was a replacement. Some physicists worry that the Standard Model is the epicycle situation, that the framework of point particles, quantum fields, and the current conception of space and time is the wrong language for describing nature at the deepest level, that the new physics waiting beyond the current detection limit won't fit neatly onto the current framework, but will require a completely different mathematical starting point. String theory was once hoped to provide that starting point. It replaces point particles with one-dimensional strings vibrating at different frequencies, naturally incorporating gravity alongside quantum mechanics. It predicts the existence of extra spatial dimensions and a vast landscape of possible universes with different physical laws. But it makes predictions at energy scales many orders of magnitude beyond any foreseeable experiment, making it currently untestable. The physics community is genuinely divided about whether string theory is the future of fundamental physics or an elegant mathematical dead end. The honest answer to the question of whether the Standard Model is fixable or replaceable is that nobody knows. The answer depends on what the anomalies currently showing up in the data turn out to be. If the new physics discovered by the high luminosity upgrade is a new particle or force that fits naturally into an extended quantum field theory, the Standard Model gets extended. If the new physics is stranger, if it points towards structures that resist incorporation into the current framework, the replacement scenario becomes more compelling. Physicists are genuinely afraid of the replacement scenario, not because they don't want to discover new physics, but because a replacement would mean decades of theoretical work built on the current framework needs to be revisited. Careers spent developing particular mathematical tools might turn out to be irrelevant to the actual structure of the universe. The intellectual cost of a paradigm replacement is enormous. And yet, every major revolution in physics required exactly that cost. And every revolution produced a deeper, more powerful understanding of reality than what it replaced. The collider is at this moment generating the data that will eventually answer the question. The high luminosity era will run through the late 2030s and into the 2040s. During that time, physicists will collect more collision data than in all previous decades of accelerator physics combined. Every open question currently sitting at the edge of the Standard Model will be pushed to its limit. Dark matter searches will either find something or rule out the most plausible candidates completely. The kaon and B meson anomalies will either become confirmed discoveries or fade into the background. The Higgs boson's mass will be pinned to a precision that settles the stability question. The dark sectors will either reveal new structures or demonstrate their absence up to the machine's maximum reach. At the end of that program, physicists will know far more than they do today. But they already know that whatever they find, it won't be the final answer. Every discovery in physics history has opened more questions than it closed. The discovery of the electron revealed the atom's structure but prompted 50 years of work to understand quantum mechanics. The discovery of quarks solved the mystery of why there were so many different hadrons, but launched decades of work on the strong force. The Higgs boson confirmed the mechanism of mass generation, but raised the stability question and left dark matter completely unexplained. The physics community is already in early discussions about what comes after the high luminosity era. A next generation of colliders is being proposed at several scales. One concept, being developed through an international collaboration, would be a circular machine with a circumference of nearly 100 kilometers, more than 3 times longer than the current tunnel, capable of reaching collision energies many times higher than anything achievable today. This machine would take decades to build and cost more than any physics instrument ever constructed. Another concept proposes using laser-driven plasma waves to accelerate particles, potentially achieving the same collision energies in a machine physically small enough to fit inside existing buildings. This technology exists in prototype form, but requires decades of development before it could reach the energies needed for fundamental physics. A third approach focuses on colliding muons instead of protons. Muons are heavier cousins of electrons, and muon collisions produce cleaner signals than proton collisions because muons are point-like particles rather than composite ones made of quarks. A muon collider could reach very high effective energies in a compact ring. The technical challenges are extreme since muons decay in microseconds. But the physics case is compelling. Each of these machines represents a choice about what questions to prioritize. The choice depends on what the high luminosity era finds. If specific new particles appear at accessible energies, the next machine gets designed to study them in detail. If the result is absence, the next machine needs to reach higher energies to push into unexplored territory. The decision about which machine to build will be made by the scientific community sometime in the 2030s, informed by data that doesn't fully exist yet. What physicists agree on is this. The questions now sitting unanswered are not technical details. They are questions about the fundamental nature of matter, energy, space, and time, about why the universe exists in the form it does, about whether the laws of physics are stable across the entire cosmos or just stable in our corner of it. The machine buried under Europe is one step in a search that will outlast every person currently working on it. The universe has been hiding its deepest rules for 13.88 billion years. Physicists have been asking questions for a few centuries. The conversation is just beginning. And here's the part that should genuinely unsettle you. The people who understand this best, the ones who have spent their entire careers inside the mathematics, who have built the detectors and analyzed the data, who know the standard model the way a musician knows an instrument, are not relaxed about what they're seeing. They're careful in public. They use measured language. They emphasize uncertainty and the need for more data. But in private conversations, in conference corridors, in the small hours after a new result comes out, the tone changes. They talk about the possibility that the universe is not what it appears to be, that the solid ground of physics, the framework that has guided every technological advance from transistors to GPS to medical imaging, might be sitting on something hollow, that the rules we've discovered are not the rules. They're an approximation, a local phenomenon, a description of one small corner of a much stranger reality. The kaon anomalies, the B meson deviations, the Higgs mass sitting at the edge of stability, the dark matter that won't show up, the dark energy that shouldn't exist, the matter-antimatter asymmetry that has no explanation, the cosmological constant that's wrong by 120 orders of magnitude. Each of these is a crack in the facade, and they're all pointing in the same direction. Something is down there, below the atom, below the quark, below the scale where any instrument has ever reached. Something that is shaping the universe we see, bending the rules we've discovered, tipping the balances that determine whether matter survives, whether stars form, whether life can exist. The physicists don't know what it is. They have theories, they have candidates, they have mathematical frameworks that might describe it, but they don't know. And the machine that might find it is currently being taken apart and rebuilt piece by piece to be made 10 times more powerful. When it comes back online, the search resumes. The data will flow. The statistics will accumulate. The anomalies will either grow into discoveries or fade into noise. And one way or another, the next decade will answer questions that humanity has been asking since the first person looked up at the stars and wondered why anything exists at all. The answers might be comforting. The universe might turn out to be stable. The anomalies might resolve into a new particle that fits neatly into an extended framework. The standard model might get a patch, and physics might continue on its steady march. Or the answers might be something else entirely, something that requires rewriting every physics textbook on Earth, something that reveals the vacuum of space to be a fragile thing, balanced on a knife's edge. Something that explains why the universe is the way it is by showing that it could so easily have been otherwise. The machine is quiet now. The tunnel is empty. The technicians are working in the cold, replacing magnets and upgrading detectors. But beneath the surface, beneath the engineering and the logistics and the project management, there is a current of anticipation that the people involved feel every day. They're about to turn on the most powerful instrument ever built, and they have no idea what it's going to find. Neither do you. Neither does anyone. The universe has been keeping its secrets for 13.8 billion years. The next chapter is about to begin. The tunnel is cold. Not just cold in the way a basement is cold, but cold in the way that requires industrial machinery to maintain. The superconducting magnets that line the 27-kilometer ring need to stay at minus 400 to 456 degrees Fahrenheit to function. That's colder than the surface of Pluto, colder than most of deep space. The liquid helium that cools them circulates through a system so vast and so precisely engineered that it could refrigerate a small city. Right now, that system is partially warmed. The magnets are being replaced. The detectors are being upgraded. The tunnel is filled with the sound of work, of tools and machinery and human voices echoing off concrete walls that have seen some of the most extraordinary events in the history of science. But the work won't last forever, and when it's done, the cold will return. The beams will start circulating, the collisions will begin, and the data will start flowing. The data is what matters. The data is the voice of the universe. And the universe has been trying to tell us something for years now, something that we're only just beginning to understand. Let's go back to the beginning of the story. Not the beginning of the universe, but the beginning of our attempt to understand it. In the early 20th century, physicists discovered that the atom was not indivisible. It was made of smaller particles, protons, neutrons, electrons. Then they discovered that protons and neutrons were made of even smaller particles, quarks. Then they discovered that there were 6 types of quarks, 6 types of leptons, and a set of force-carrying particles that mediated the interactions between them. By the 1970s, all of these discoveries had been woven into a single theoretical framework. The Standard Model of Particle Physics, a set of equations that described every known particle and 3 of the 4 fundamental forces. It was elegant, it was powerful, it was the most successful scientific theory in history, but it was incomplete. Even as it was being formulated, physicists knew it had gaps. It couldn't explain gravity. It couldn't explain dark matter. It couldn't explain dark energy. It couldn't explain why the universe is made of matter instead of antimatter. These gaps were known, they were discussed, but they were also set aside. The Standard Model worked so well for everything it could describe that physicists hoped the gaps would be filled by extensions, new particles, new forces, new symmetries, something that would complete the picture. The Large Hadron Collider was built to find those extensions. It was built to discover the new physics that would fill the gaps. It was built to answer the questions that the Standard Model couldn't. And for a while, it seemed to be working. In 2012, the collider discovered the Higgs boson, the last missing piece of the Standard Model. The discovery was celebrated around the world. The rulebook was complete. The picture was full. But then the questions started. The Higgs boson's mass was not what physicists expected. It was sitting in a dangerous zone, a zone that suggested the vacuum of space might be metastable, a zone that suggested the universe might be balanced on a knife's edge. And then the anomalies started. Small deviations from Standard Model predictions, deviations that showed up in rare particle decays, deviations that kept appearing in the same direction across multiple experiments. The deviations were not large. They were barely measurable, but they were consistent. And consistency is what physicists look for. Random errors scatter in all directions. Systematic signals point the same way every time. The data was pointing, and the pointing was making physicists nervous. Let's talk about what the data is actually showing. The most significant anomaly comes from the Na-62 experiment, which studies the decay of kaons. Kaons are particles that contain strange quarks. They're produced in the collisions at the collider, and they decay through the weak nuclear force. The specific decay that Na-62 is studying is extraordinarily rare. A positively charged kaon breaking apart into a positively charged pion, a neutrino, and an antineutrino. The Standard Model predicts this should happen once in every 10 billion kaon decays. The Na-62 team measured the rate, and the rate was higher than the Standard Model predicts. Not by a lot, but consistently, in a way that suggests something is influencing the decay. What could be influencing it? A new particle, a new force, something from a layer of reality that we haven't seen yet. Something that the Standard Model doesn't account for. The Kodo experiment in Japan is studying a similar decay, a neutral kaon breaking apart into a neutral pion, a neutrino, and an antineutrino. This decay is even rarer. The Standard Model predicts it should happen roughly 3 times in every 100 billion neutral kaon decays. Kodo has also seen more events than the Standard Model predicts. The excess was initially exciting, then partially explained by background effects, but the mystery didn't disappear. The hunt continued, and then there are the B meson anomalies. B mesons are particles that contain bottom quarks. They decay in ways that the Standard Model predicts with great precision. But the measurements are showing deviations that point in the same direction as the kaon anomalies. 7 specific particle interactions, 7 types of particle decay. The physics community calls them the Magnificent Seven, and they're all showing hints of something beyond the Standard Model. The hints are not yet confirmed, the statistical significance is not yet high enough, but the pattern is there, and the pattern is hard to dismiss. What could explain the pattern? Several possibilities are being seriously studied. One possibility is a leptoquark, a particle that mediates interactions between quarks and leptons. The Standard Model doesn't include leptoquarks, but they appear in many extensions of the Standard Model, and they could explain the B meson anomalies. Another possibility is a Z prime, a heavy version of the Z boson, the particle that mediates the weak nuclear force. A Z prime could explain the kaon anomalies. It could also explain some of the B meson deviations. Another possibility is additional Higgs-like particles. The Standard Model includes one Higgs boson, but many extensions of the Standard Model predict additional Higgs particles. These particles could influence rare decays in ways that the Standard Model doesn't account for. Another possibility is sterile neutrinos. Neutrinos that don't interact through any of the known forces except gravity. Sterile neutrinos could explain dark matter. They could also explain the matter-antimatter asymmetry, and they could influence rare decays in subtle ways. Each of these possibilities makes specific predictions. Each of them can be tested, and the high luminosity upgrade of the collider is designed to test them. If a leptoquark exists in the mass range that the anomalies suggest, the upgraded machine should produce it. If a Z prime exists, it should show up as a resonance in the collision data. If additional Higgs-like particles exist, they should appear in the decay products of the Higgs boson. If sterile neutrinos exist, they should show up as missing energy in certain decays. The machine is being rebuilt to find these particles. And if they exist, the machine will find them. But what if they don't exist? What if the anomalies are caused by something even stranger? Something that doesn't fit into any of the current theoretical frameworks? This is the possibility that keeps physicists up at night. The possibility that the new physics, when it's discovered, will be so strange that it will require a complete rethink of the foundations of physics. The possibility that the universe operates on rules that we haven't even begun to imagine. The history of physics suggests that this is a real possibility. Every time scientists thought they had the universe figured out, the universe surprised them. The discovery of quantum mechanics in the 1920s was a shock. The discovery of the expanding universe in the 1920s was a shock. The discovery of dark matter in the 1970s was a shock. The discovery of dark energy in the 1990s was a shock. Each of these discoveries required a fundamental revision of our understanding. Each of them revealed that the universe is stranger than we thought. Each of them opened new questions that we hadn't even formulated before. The next discovery might be the same. It might reveal that the universe is even stranger than we think. It might reveal that there are dimensions of reality that we haven't even imagined. It might reveal that the vacuum of space is not what we think it is. It might reveal that the very fabric of reality is different from what we believe. Let's think about what that might mean. Let's think about the possibility that the vacuum of space is not stable. The vacuum is not empty. It's a seething field of energy. Particles constantly blink in and out of existence. Fields permeate all of space, and every field has an energy state. The lowest possible energy state is called the true vacuum. A field not sitting at its true vacuum is sitting at a higher energy called a false vacuum. The Higgs field, the invisible energy field that gives all particles their mass, might be sitting in a false vacuum. The measured mass of the Higgs boson, about 125 gigaelectron volts, places the universe in a metastable zone, a zone where the vacuum appears stable but isn't. a zone where the vacuum could, in principle, tunnel to a lower energy state. If that happened, the consequences would be catastrophic. A bubble of true vacuum would nucleate at a point in space and expand outward at the speed of light. The bubble wall would carry with it a region where the laws of physics are fundamentally different, where the strengths of forces, the masses of particles, and the rules governing chemistry and biology are all different from everything inside. Everything the bubble wall touched would be converted instantly. You would not see it coming. Light from the approaching wall couldn't outrun the wall. This is the scenario that physicists call vacuum decay. It's the ultimate cosmic reset. The universe doesn't get destroyed in the way a bomb destroys a building. It gets converted, replaced by a different set of physical laws, building an entirely different kind of universe behind it. The time scale for such an event, if the metastable interpretation is correct, is likely to be vastly longer than the current age of the universe, potentially trillions upon trillions of years. But the possibility exists, and the fact that it exists is deeply unsettling. Now, here's the connection that makes this even more unsettling. The same physics that makes the vacuum metastable might be connected to the other anomalies. The same new particles or forces that could explain the kaon anomalies might also stabilize the Higgs field. The same physics that explains dark matter might also explain why the vacuum hasn't collapsed. The same mechanism that tipped the balance between matter and antimatter might also determine the fate of the universe. The cracks in the standard model might not be separate problems. They might be symptoms of a single underlying cause, a deeper layer of reality that we haven't seen yet, a layer that, once discovered, would explain everything. This is what the physicists are chasing. This is what the high luminosity upgrade is designed to find. And this is why the silence in the tunnel right now is so charged with anticipation. Let's think about what the discovery of new physics would actually look like. Not in terms of the physics, but in terms of the process. The first step would be the accumulation of data. The upgraded machine would start producing collisions at 10 times the current rate. The rare decays that carry the signals of new physics would start appearing in larger numbers. The statistical significance of the anomalies would start to grow. If the anomalies are real, they should cross the 5 sigma threshold within a few years of running. 5 sigma is the gold standard for discovery in particle physics. It means the probability of the result being a random fluctuation is less than 1 in 3 million. When the 5 sigma threshold is crossed, the discovery is announced. The announcement would be made at a major conference. The paper would be published in a leading journal. The physics community would erupt in excitement. But the announcement would not be the end of the story. It would be the beginning. The discovery of new physics would open a new chapter in our understanding of the universe. It would raise new questions. It would require new theories. It would lead to new experiments. The discovery would also have practical implications. Every major advance in fundamental physics has eventually led to technologies that transformed human civilization. The discovery of electromagnetism led to the electric grid. The discovery of quantum mechanics led to the transistor. The discovery of nuclear physics led to nuclear power. The discovery of new physics beyond the standard model would almost certainly lead to technologies that we can't imagine today. But the practical applications are not the most important thing. The most important thing is the knowledge itself. The knowledge that the universe is more complex than we thought. The knowledge that there are particles and forces that we haven't discovered yet. The knowledge that the standard model is not the final word. This knowledge is valuable in itself. It's valuable because it expands our understanding of reality. It's valuable because it reminds us that there is always more to learn. It's valuable because it keeps us humble. The physicists working on the Large Hadron Collider are not just doing a job. They are participating in one of the greatest intellectual adventures in human history. They are probing the fundamental nature of reality. They are asking questions that have never been asked before. They are pushing the boundaries of human knowledge, and they are doing it with a machine that is itself a testament to human ingenuity. A machine that can accelerate protons to 99.9999% of the speed of light. A machine that can recreate the conditions that existed a fraction of a second after the Big Bang. A machine that can detect particles that exist for only a tiny fraction of a second before decaying. A machine that has to correct for the gravitational pull of the moon just to keep its beams on track. The machine is a marvel, but it's also a tool for answering questions. And the questions it's being rebuilt to answer are the biggest questions there are. That why does the universe exist? Why is it made of matter instead of antimatter? What is dark matter? What is dark energy? Is the vacuum of space stable? Are there particles and forces we haven't discovered yet? Is the Standard Model the right framework for understanding reality, or is it just an approximation? These are not abstract questions. They are questions about the nature of existence itself. They are questions about why we're here. They are questions that have been asked by every civilization, every religion, every philosophy, and now for the first time in history, we have the tools to answer them. The tools are being rebuilt right now. The machine is being upgraded, the detectors are being replaced, the trigger systems are being improved, and when the work is done, when the machine is turned back on, the search will resume. The search for the truth about the universe. The search for the rules that govern reality. The search for the answers to the questions that have haunted humanity since the beginning. The search is about to enter its most exciting phase, and the people who will be conducting it know that they are standing on the edge of something enormous, something that could change everything, something that could reveal the deepest secrets of the cosmos. They don't know what they'll find. Nobody does. But they know that whatever it is, it will be worth the wait. It will be worth the years of work. It will be worth the silence in the tunnel, because the silence is about to be broken. And when it is, the universe will speak, and we will listen. Let's think about what the universe might say. Let's think about the possibilities. The most likely outcome, statistically speaking, is that the anomalies will resolve into something mundane. The kaon deviation might turn out to be a subtle background effect that wasn't fully accounted for. The B meson deviations might fade as more data accumulates. The Higgs mass might shift slightly with better measurements, moving the stability calculation into the safe zone. The dark matter searches might continue to come up empty, pushing the particle explanation into ever more exotic corners. This is the boring outcome. The outcome where the Standard Model survives, at least for now. The outcome where the search continues, but without a breakthrough. But there's another outcome, the exciting outcome. The outcome where the anomalies are real, where the kaon decay rate really is higher than the Standard Model predicts, where the B meson deviations really are caused by new physics, where the Higgs mass really is sitting at the edge of stability because something is holding it there, where dark matter really is made of particles that we're just beginning to detect. This is the outcome that would change everything. This is the outcome that would open a new chapter in physics. This is the outcome that the physicists are hoping for, even as they maintain their professional skepticism. If this outcome comes to pass, what would it look like? What would the new physics be? The leading candidates are already being discussed. A leptoquark, a particle that mediates interactions between quarks and leptons, could explain the B meson anomalies. A new heavy particle, sometimes called a Z prime, could explain the kaon deviation. Additional Higgs-like particles could explain the stability of the vacuum. Sterile neutrinos could explain both dark matter and the matter-antimatter asymmetry. Each of these candidates makes specific predictions. Each of them can be tested, and the high luminosity upgrade is designed to test them. If a leptoquark exists in the mass range that the anomalies suggest, the upgraded machine should produce it. If a Z prime exists, it should show up as a resonance in the collision data. If additional Higgs-like particles exist, they should appear in the decay products of the Higgs boson. If sterile neutrinos exist, they should show up as missing energy in certain decays. The machine is being rebuilt to find these particles, and if they exist, the machine will find them. But what if they don't exist? What if the anomalies are caused by something even stranger? Something that doesn't fit into any of the current theoretical frameworks? This is the possibility that keeps physicists up at night. The possibility that the new physics, when it's discovered, will be so strange that it will require a complete rethink of the foundations of physics. The possibility that the universe operates on rules that we haven't even begun to imagine. The history of physics suggests that this is a real possibility. Every time scientists thought they had the universe figured out, the universe surprised them. The discovery of quantum mechanics in the 1920s was a shock. The discovery of the expanding universe in the 1920s was a shock. The discovery of dark matter in the 1970s was a shock. The discovery of dark energy in the 1990s was a shock. Each of these discoveries required a fundamental revision of our understanding. Each of them revealed that the universe is stranger than we thought. Each of them opened new questions that we hadn't even formulated before. The next discovery might be the same. It might reveal that the universe is even stranger than we think. It might reveal that there are dimensions of reality that we haven't even imagined. It might reveal that the vacuum of space is not what we think it is. It might reveal that the very fabric of reality is different from what we believe. Let's think about what that might mean. Let's think about the possibility that the Standard Model is not just incomplete, but fundamentally wrong. The Standard Model is a quantum field theory. It describes particles as excitations of underlying fields. It describes forces as the exchange of particles. It has been tested to extraordinary precision. But it might not be the right framework for describing nature at the deepest level. Some physicists believe that the Standard Model is like the epicycles of Ptolemaic astronomy. It works well for what it describes, but it's built on the wrong foundation. The epicycles could predict the positions of the planets with remarkable accuracy, but they were ultimately replaced by the heliocentric model, which was simpler and more accurate. The Standard Model might be the same. It might be a very good approximation of a deeper reality, but the deeper reality might be fundamentally different from what the Standard Model describes. What could that deeper reality be? Several possibilities are being explored. String theory proposes that the fundamental constituents of nature are not point particles, but one-dimensional strings. The different particles we observe are different vibrational modes of these strings. String theory naturally incorporates gravity alongside quantum mechanics. It predicts the existence of extraspatial dimensions, but it makes predictions at energy scales far beyond any conceivable collider. Loop quantum gravity proposes that space itself is quantized. That space is made of discrete units, like pixels on a screen. This theory attempts to unify general relativity with quantum mechanics, but it makes predictions that are difficult to test. Causal set theory proposes that the fundamental structure of space-time is a discrete set of points ordered by causality. This theory attempts to explain why space-time has the properties it does, but it's still in its early stages. None of these theories has been confirmed. Each of them is speculative, but they represent the possibility that the Standard Model is not the final word. They represent the possibility that the universe is even stranger than we think. The high luminosity upgrade of the collider won't directly test these theories, but it might find evidence that points in their direction. It might find particles or forces that don't fit into the Standard Model. It might find patterns in the data that suggest a deeper structure. It might find something that no one has predicted. This is the exciting possibility. The possibility that the next decade will reveal something truly revolutionary. The possibility that the next decade will change not just physics, but our entire understanding of reality. The physicists working on the machine are hoping for this. They're hoping for a discovery that will shake the foundations of their field. They're hoping for a discovery that will be remembered for centuries. They're hoping for a discovery that will answer the questions that have haunted humanity since the beginning. And they're willing to wait for it. They're willing to spend years rebuilding the machine. They're willing to spend years analyzing the data. They're willing to spend years chasing the anomalies, checking the calculations, testing the theories, because they know that the answers are out there. Or rather, down there, buried in the collisions that will happen when the machine turns back on, buried in the data that will flow from the detectors buried in the patterns that will emerge from billions upon billions of particle interactions? The answers are waiting, and the machine is being rebuilt to find them. Let's think about what the next few years will look like. The shutdown is scheduled to last until approximately 2029. During that time, the machine will be transformed. The magnets will be replaced. The detectors will be upgraded. The trigger systems will be improved. The infrastructure will be modernized. When the machine comes back online, it will be more powerful than ever before. The collision rate will be 10 times higher. The data flow will be 10 times greater. The sensitivity will be 10 times better. The first data from the upgraded machine will be analyzed immediately. The physicists will be looking for the same anomalies that have been tantalizing them for years: the kaon decay rate, the B meson deviations, the Higgs mass, the dark matter searches. If the anomalies are real, they should start to become more significant within the first few years of running. The statistical uncertainty will shrink as more data accumulates. The deviations will either grow or fade. The truth will start to emerge. If the anomalies grow, the excitement will build. Papers will be published. Conferences will be held. The physics community will start to take the possibility of new physics seriously. The search for the new particles or forces that explain the anomalies will intensify. If the anomalies fade, the disappointment will be real, but the search will continue. The physicists will look for other signals. They'll explore other regions of parameter space. They'll push the machine to its limits. Either way, the next decade will be one of the most exciting periods in the history of physics. The machine will be running at full power, the data will be flowing, the discoveries will be made, and the discoveries will change how we understand the universe. Let's think about what those discoveries might be. The most likely discovery, if the anomalies are real, is a new particle. A particle that doesn't fit into the standard model. A particle that would require an extension of the framework. The particle could be a leptoquark. It could be a Z prime. It could be a sterile neutrino. It could be something else entirely, something that no one has predicted, something that will require new theories to explain. The discovery of a new particle would be a landmark event. It would be the first new particle discovered since the Higgs boson in 2012. It would confirm that the standard model is incomplete. It would open a new chapter in physics. But the discovery of a new particle is not the only possibility. The anomalies could also be caused by a new force, a force that doesn't fit into the standard model, a force that operates at scales we haven't probed before. The discovery of a new force would be even more revolutionary. It would mean that there are fundamental interactions in the universe that we haven't discovered yet. It would mean that the four known forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, are not the whole story. A new force could explain the kaon anomalies. It could explain the B meson deviations. It could explain the dark matter. It could explain the matter-antimatter asymmetry. It could explain the stability of the vacuum. A new force would be the discovery of a lifetime. It would be the kind of discovery that physicists dream about. It would be the kind of discovery that would be remembered for centuries. And it's possible. The anomalies are consistent with the existence of a new force. A force that is weak enough to have escaped detection so far, but strong enough to influence the rare decays that the collider is measuring. If such a force exists, the upgraded machine should be able to detect its effects. The deviations from the standard model predictions should grow as more data accumulates. The pattern of deviations should become clearer. The nature of the new force should start to emerge. This is the exciting possibility. The possibility that the next decade will reveal a new force of nature. The possibility that the next decade will change physics forever. But there's an even more exciting possibility. The possibility that the anomalies are connected to the deepest mysteries of the universe. The possibility that the same new physics that explains the kaon anomalies also explains dark matter. The possibility that the same new physics that explains the B meson deviations also explains the matter-antimatter asymmetry. The possibility that the same new physics that explains the Higgs mass also explains the stability of the vacuum. If all the cracks in the standard model are connected, if they all point to the same underlying cause, then the discovery of that cause would be the greatest scientific discovery in history. It would be bigger than gravity, bigger than relativity, bigger than quantum mechanics. It would be the discovery that unifies our understanding of the universe. This is what the physicists are hoping for. This is what the machine is being rebuilt to find. This is what the next decade might bring. The silence in the tunnel is about to be broken. The machine is about to be turned back on. The search is about to resume, and the answers are waiting. Let's think about what those answers might mean for humanity. If the next decade reveals new physics, if the anomalies are confirmed as real, if new particles or forces are discovered, the impact will be felt far beyond the physics community. The discovery will be front-page news. It will be discussed in classrooms, in boardrooms, in living rooms. It will change how people think about the universe. Some people will be excited. Some people will be confused. Some people will be afraid. The discovery of new physics will challenge our understanding of reality. It will raise questions that we don't have answers to. It will remind us that the universe is stranger and more complex than we thought. But it will also be an opportunity to learn, an opportunity to grow, an opportunity to expand our understanding of the cosmos. The discovery of new physics will open new avenues of research. It will lead to new technologies. It will lead to new ways of thinking about the universe. It will lead to new questions that we can't even formulate yet. The history of science shows that fundamental discoveries always lead to practical applications. The discovery of electromagnetism led to the electric grid. The discovery of quantum mechanics led to the transistor. The discovery of nuclear physics led to nuclear power. The discovery of new physics beyond the standard model will almost certainly lead to technologies that we can't imagine today. The machine is being rebuilt. The search is about to resume. The answers are waiting, and we are about to find them.